Okay, guys. Again, my apologies for Wednesday. I'm still kind of but I'm here, and you really want to be here too, right? I know. So thank you. And again, my apologies. I finished chapter 15 on Monday, and I did spherical coordinates, and we did integration in spherical coordinates. I tried to give you a sense of what that volume element meant. Now, at some level, just to do the calculation, you don't need to know where it came from, right? You just need to know what it is. Okay? So the question is, do you need to memorize this formula? What's this formula? And I don't recall if I left it for you on the board, because I constructed the inverse. This is the transformation from spherical polar to Cartesian coordinates. This is the inverse of the transformation that I wrote down on Monday. Do you need to memorize that formula? Yeah, you do. Yeah, you do. And why? Because in knowing this formula, it will show that you understand what a spherical representation is. So notice that rho sine phi is the distance from a point to the z-axis. That's the cylindrical r. That's the cylindrical r. So this is cylindrical r cos theta, r sine theta. So the cos theta and the sine theta come naturally from trigonometry. And this is, well, you just construct it the other way, right? It's since phi is the angle from the north polar axis, rho cos phi is the z component. And you can see x squared plus y squared, because of Pythagoras' theorem, these guys add up, and you're left with rho squared sine squared phi, plus z squared, you're left with rho squared cos squared phi, plus rho squared sine squared phi is rho squared. So x squared plus y squared plus z squared is rho squared, falls naturally out of these. So this is the inverse transformation. So this is polar, spherical polar, to Cartesian. So you need to know this transformation. It's important. It is such a common coordinate system that you need to know it. And you need to know that the volume element in polar coordinates, in spherical polar coordinates, is rho squared sine phi d rho d phi d theta. Okay? So, yeah, there are some things you need to just straight up memorize. And that's it, okay? I hope my discussion gave you a sense of where it came from, but nonetheless, you just have to memorize it. Now, that being said, I'm moving to chapter 13. I'm moving to chapter 13 because I think next week is week 6 or whatever it is. Got a lot of holidays in November, and we need to get to chapter 16. And I want us to move forward. This material will not be on the midterm exam, which is on Monday, of course. The midterm is on Monday. The material will not be on that exam. Okay? So chapter 13 is the study of curves. Chapter 13, we will study curves. Curves in space, as they say. I was a Muppets fan as a child. Pigs in Space. Does anyone remember Pigs in Space? Miss Piggy. I'm too old. Muppets are not cool anymore. They were never cool, but that's curves in space. We need to understand curves, okay? Now, we're going to be doing a lot of things in 3 dimensions, but you guys have spent a lot of time thinking in 2 dimensions. So I want to outline two curves. And let me just say, in this class, you need to know 2 curves very well. The line and the circle. Okay, sounds almost ridiculous, but you need to know the line and the circle. And we will find out that when you add these 2 things together in 3 dimensions, you'll get a nice third curve called the helix. And so we're going to spend some time talking about those 3 curves. Okay? What I want to outline for you today is 3 algebraic ways that we know to represent these curves. You have experience with at least 2 of them, probably 3 of them. Okay? We have algebraic forms, algebraic representation. How do I look at these curves? Representations. We have three 3 of them. So there's 2 plus 1 curves and 3 representations. The first representation I will call the explicit representation. Explicit representation. Representation. Okay? For example, the explicit representation of a line is y, so e.g., y equals 3x plus 2. That's the explicit representation of a line. How do I draw this? Well, I look at it in the xy plane, and we recall, we memorized probably by now that y equals mx plus b is the quick way to read off, m being the slope, b being the y-intercept. And so we know that this is a line with intercept at 0, 2 from here. That is to say when x is 0, y is 2. And it has slope 3. So when you go over 1, it's a very slopey line. It's like this, okay? That's an explicit representation of a line. I will give you, okay, so that's one representation. We have explicit representations of parabolas, e.g., y equals x minus 2 quantity squared, right? And we know that, oh, this is a parabola whose vertex is at 2, 0, and it opens upward. It's like that. We've learned some properties. You know, if the canonical parabola is y equals x squared, so if I replace x by x minus 2, that's like shifting it to the right 2. If I add a 1 here, that's like shifting it up 1. If I multiply by a negative, it's like flipping the whole thing down. We know these kinds of, we know how to look at some explicit representations and read off the shape pretty quickly, okay? And that's really what you need to get adept with, right, is reading off some shapes pretty quickly. So that's the parabola. The second representation that you have experience with, too, is the implicit representation. Now, so for example, an explicit representation explicitly says one variable is determined in terms of the other ones. And so we talked about independent and dependent, right? We learned independent, x is independent, y is dependent. But of course, when you have a relationship of dependence there, it's somewhat arbitrary to say that y is dependent on x. I could have written that as x equals y minus 2 divided by 3, and it would be the same curve, right? It would be the same thing. I've just decided that x is dependent. So what is independent and what is dependent is sort of context dependent. Okay. The implicit representation, in effect, recognizes that. Okay? And it says sometimes you have everybody wrapped up together. Now, we rarely see implicit representations of lines. Well, that's not even true. That's not even true. I guess we do see implicit representations of a line. Here's an implicit representation of a line, just for fun. E.g., y minus 3 over x minus 2 equals 1/2. Okay? You may recognize this as a particular realization of the point-point form of the line. Do you remember the point-point form of the line? Little bubble of memory going back, dusting off the cobwebs. Y minus y0 over x minus x0 equals y1 minus y0 over x1 minus x0. And this says, well, hey, if you were given 2 points, x1 comma x0 comma y0 and x1 comma y1, this is the equation for the line that goes through those 2 points. Okay? This is called the point-point form of the line. That's the slope-intercept form of the line over there. And if I were to take this literally, I would just plug it in. Here I plugged in x0 is 2 comma 3, and don't let me calculate what x1 and y1 are. I can't do subtraction. X1 is 4. Y1 is 4. 4, 4. Goes through 2, 3, and 4, 4. I think. But so if you were to look at this, this is an implicit form because y and x are mixed up in here. And what you would do usually is say, well, I write it this way first, and then I multiply, right? I multiply by x minus 2, and so I'm left with x over 2 minus 2 over 2, which is minus 1, plus 3, and then I solve it. Now I have an explicit form. Okay? But this is truly an implicit form. I have to solve an equation. Not very hard solution, but nonetheless, I'm solving an equation. Okay? And if you have it in this form, you always worry about, oh, what happens when x goes to 2? Be careful when x goes to 2, right? You know, what's going to happen over here? But nothing happens bad. This is fine. This is just fine. But that is an implicit representation. We don't usually leave lines in their implicit representation. If I were to say, what's the most common implicit representation of a curve that you encounter in your life thus far as budding mathematicians and engineers? What's that? The circle, right? The circle is the most common one. So e.g. the circle of radius 1, for example, right? And we know what that is. X squared plus y squared equals 1. And this really tells you, hey, look, who depends on who? I don't know. They depend on each other. That's what an equation says. They depend on each other. Nobody's independent and nobody's dependent in this case, okay? Of course, this object, by the way, I'm just going to tell you this, and this object is one of a family of objects, okay? This is one of a family of objects. So, e.g., the conic sections. I want to just mention this right now. I learned this in high school, and a lot of people don't learn this stuff in high school, so I don't know. The conic sections are all represented sort of in this way. So if I say conic sections, do people, just give me a sense. Am I talking to people who know what I'm saying? Conic sections, yes. Conic sections, no. OK, so we have some chat. OK. Hmm?
Is that like the hyperbolas and all that?
Right.
All that stuff like elliptoids?
Soids.
Oh.
Yes. But yes, the answer is yeah, that is like that. In fact, that is that. So the idea is that if you take a cone, a general cone, and cut it with a plane, right? If you cut it horizontally with a plane, right, you will get a circle. Okay, the intersection of a cone and a horizontal plane is a circle. If you can't that, if you tip this, first you get the circle, then you can get an ellipse. Okay? So if you tip it at all, you get an ellipse. That's a terrible circle, please. I'm sorry. But just imagine that cone, plane, circle, tip it, get ellipse, tip it some more so that you're parallel, right? So that you're running parallel to one of these sides. You get a parabola. And tip it some more so that you're effectively vertical. You get a hyperbola. These are the conic sections, okay? Because you're cutting a section of a cone. They're all represented algebraically by what's called a quadratic form. So the quadratic form, the general quadratic form is the general implicit equation. I'm just going to try to write the most general one. ax squared plus bxy plus cy squared plus dx plus ey plus f is equal to 0. This is a general quadratic form. Okay? That's a general quadratic form. Okay? And just so you know, what makes it a quadratic form is that the highest power is 2. Okay? Its highest power is 2. So there's a quadratic in x, there's a quadratic in y at most, and there could be an xy term. Okay? A, B, C, D, E, and F play the role of m and b from the other equations. Okay? The slope and the intercept. So the point here is that you can make simple coordinate transformations by shifting your origin, okay, and by making a rotation of your axes, so that you could get this into a standard form of the circle, ellipse, hyperbola, parabola. So this represents a shifted and rotated conic section. I think this is a nice, okay? And why is this nice? Well, these are important shapes. These are basic shapes, right? And they sort of form basic archetypes in our mind for observing more complicated shapes. So it's just like the line is a very basic shape, and you go to the next less basic shape, okay? So I think if anybody is bored on a Saturday night, think about that right there and how you can make transformations of this, okay? How you can make transformations of this and how you can think about this. By the way, here's a simple example. Set B, C, D, and F equals 0. A is equal to 1 and E is equal to -1. You clearly have a parabola, right? And then you can see where the circle's hiding in here. Let me just tell you that these are the shift terms. These are the terms that you can remove by making shifts of your coordinates. And this is the rotation term right here. This is the term you can remove by making rotations, okay, of your coordinate system. So, yeah, for example, here's an ellipse. An ellipse that's centered way over here can be expressed as a polynomial of this form. Okay? So those are two representations. I see a lot more people today. If a lot of people came to get information for the midterm, it's just not going to happen in class. So if you feel like this is not going anywhere and you need to go, that's fine. I'm not going to be offended. So these are two representations that I've talked about. The implicit representation, there's the implicit representation for the circle. Notice one thing that's typical of implicit representations is that typical implicit representations are really good for these closed objects or these objects that don't satisfy a vertical line test. Okay? They don't satisfy a vertical line test. Okay? The third representation, number 3, is the parametric representation. Okay? Now, I don't think we spend enough time talking about the parametric representation. Okay? The parametric representation is the following. The parametric representation says introduce a parameter. Now the parameters we tend to use are t, t. Okay? We tend to use t, but we use other parameters like s sometimes. But the parametric representation asks you to introduce a parameter t and write the curve, and I'm going to focus on R2, so in R2, so in 2 dimensions, as 2 functions of t. X of t, y of t. Okay? So for this original example, which I have erased, maybe I'll use this example right here. Y equals x over 2 plus 2. Let's use that. So the way you would do it is you introduce a parameter t, and I want to make this is the explicit representation. I want to make an implicit representation. So you can choose. So the first thing to say is the parametric representation is not unique. Okay? And what I mean by that is there's no one way to specify a parametrization of a curve. There are many ways, and we will actually go through a couple of fundamental ways to do that, okay? A couple of fundamental ways to do that. So there's no one way to do this. But when confronted with a simple problem like a line, what you do is say, okay, I need x to be a function of t since the line goes from negative infinity to infinity, I'm going to make t, in this case, go from negative infinity to infinity. Pardon me, I'm scooting up over there. And I'm going to make x be some function of t that I decide. You can actually choose the function of t because it's not unique. So you have not complete freedom, and we'll talk about that in a second, but you have a lot of freedom. Okay? So let me choose a simple one. Let's say x is equal to 2t. I'm going to let x equal 2t. Okay? So notice that if t goes from negative infinity to infinity, x can go from negative. I'm allowing x to go from negative infinity to infinity. And if this is true, x equals 2t, I've chosen this. I substitute it back into the explicit representation or the implicit representation, whatever I've got. In this case, I've got an explicit one. And I recognize that if x equals 2t, y is equal to t plus 2. And so this is a parametric representation of that line. Okay? And now the way you think about it is like, oh, set t equals 0. Where's the point? At t equals 0, the point is at 0, 2. So at t equals 0, you're at 0, 2, which is that point down there. Okay? T equals 1. At t equals 1, you're at 2, 3. So you're going to be at 2, 3 over here. 2, 3. And you know that when you've got 2 points on a line, you just connect the dots and you're done, right? Why do we use t as a parameter? Because we really do think of it as time, and it's extremely useful for most people to think of t as time. Okay? At time t equals 0, I'm at this point. As time t goes forward, I'm over here. I'm marching along. As time t goes to negative, I'm marching backward. Is that okay? So it's useful to think this way. Pardon me. It's very useful to think this way. Now, just to continue with this example right here, I chose a particular function of t. Okay, I chose a particular function of t. I said 2t. Well, we could choose a different parametrization. Okay? What's a different parametrization I could choose? Let x of t equal, I don't know, t cubed. Let's try x of t equals t cubed. Okay? So if x of t equals t cubed, do the same thing. I've chosen my x of t, okay? And I plug it into the next to the explicit form. And so I'm left with y of t is equal to t cubed over 2 plus 2. Now, this is the same line. This is the same line as that one. Okay? What's the difference between these two lines? Well, visually from above, nothing. Nothing is different. Right? At t equals the 2 to the 1/3. At t equals 2 to the 1/3, right? At t equals 2 to the 1/3. Is that where I want to be? No. At t equals 0, excuse me. At t equals 0, you're still at 0, 2. So at t equals 0, you're still here, right? But let's think about the difference the way this curve is traversed. Imagine t is truly time, and you are at your x of t and y of t describe your location. Say you're driving, okay? There, you're just chugging along at a constant velocity. And we'll talk about velocity in this section in a moment. Here, what happens is, at t goes to negative infinity, you're going super, super, super fast. For a small change in time, you're getting a huge change in x, and therefore a huge change in y. So you're going super, 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 super fast. As t goes to 0, you're slowing down enormously, and then you're speeding up again. So although these are the same curves, they are traversed differently. Okay? So these are parametric forms of the line. So the line is one of the basic things you need to know. One of the basic things you need to know. Okay? Well, I had already talked about the circle, so I would like to continue to talk about the circle. Okay? And I really believe that it's important that we ground our algebraic understanding, our understanding of calculus, in real things. Okay? And so the circle I want to talk about is that one right up there. Okay? The clock. Let's spend a moment talking about the clock. Okay? Okay. I want to construct this whole problem from scratch so you see all the pieces that go into it. Okay? So you see all the pieces that go into this. Okay. I'm going to need at least 2 boards, so let's start up here. Okay. E.g., parametric form of the clock. Okay? So I remember when I was a kid, you always have to define your variables. So let's start at the beginning. Let x of t and y of t be the coordinates of the second hand, hand that counts out the seconds, the second hand of a clock of radius. I'm going to use capital R for the radius of that clock at time t measured in seconds. Okay? So what I want you to think about, we need a bigger clock. What I want you to think about is this clock and it has a second hand, and a second hand is very useful as we go and think about vectors, okay? As we think about vectors, which we will do hopefully before the end of today, the second hand is very useful in thinking about those vectors, okay? And we are thinking about the location of the tip of the second hand, okay? So you watch it. You know what it's doing, okay? Unfortunately, most clocks have this kind of tick, 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 so it's a very discontinuous motion, right? So think of a more continuous clock that's actually going around, a truly analog clock that's actually going around at a constant rate, okay? I want the hand to be here at t equals 0 seconds, and I want it to come back at t equals 0 seconds. Is that okay with y'all? Now, I need to come up with a parametrization. Yes?
Why is it coming back at t equals 0 seconds and not t equals 60 seconds?
Because I'm that way. Sorry. I was always hoping to make these videos really nice that I could use them in subsequent years, but there's so many typos that I can't. Thank goodness you guys are keen, catching all my typos. Okay, so let's do this, right? It's not a very hard problem, but we just got to be careful. Some people have memorized things like the trig functions, sine and cosine and theta, and You got to be a little careful here, okay? You got to be a little careful, okay? So maybe I will construct it from scratch, beginning with an angle. Let's start with an angle, okay? So let's imagine we have the angle here, which is measured not as we traditionally measure our angles from the x-axis, but it's measured from the top, right? And it's not going to go in the counterclockwise direction, which is what we learned from trigonometry, but it's going to go clockwise because it's a clock. It better go clockwise, huh? What?
Like in pre-cal we learned bearing is from the vertical axis counter or clockwise is the bearing.
The bearing. Is it called bearing? It could be called bearing. Yeah, I guess if you're like a ship and it's your bearing, you're heading, right? Yeah, I guess it's bearing. I don't know the words for a lot of things. I just know that I got to start from scratch all the time. And if I can start from scratch, I can figure things out, you know? So I'm going to call this angle, I'm not going to call it beta for bearing. I'm not going to do that. I'll just call it theta. Okay, will you guys be okay if I call it theta? Because I know we all remember that theta is measured from not the same theta, right? It's just an angle from some axis. In this case, it'll be there, okay? That's theta. For the purposes of this discussion, that's theta, okay? It's our bearing, okay? And so there is the location of the point here, x and y, that point is located there. So this is, you're supposed to think of this as the arrow at the beginning, this is the arrow somewhat later, okay? So the first thing we note is, and by the way, the length of the arrow is capital R. So the first thing we note is we can read off of this immediately that x is the sine of theta times r, right? It's because we're measuring from the top that x has now become the sine of theta. Okay, it's usually from the side, so it's cosine of the other theta, but it's sine of this theta. Okay, so x is equal to r times the sine of theta. Right? Opposite, this is the x value, and that's the opposite from the angle. Okay? And then y is equal to r times the cosine of theta. Put these in parentheses. So here we have a form of x and y in turn. This is a parametric form, actually. This is already a parametric form of the curve, but the parameter is theta. Okay? Is this angle. Okay? But I would claim that we don't have an intuitive sense of theta. You might not like that. I still claim that a lot of students don't have an intuitive sense of what an angle is. And we don't necessarily want to measure it in terms of theta. We really want to measure it as a function of time. Okay? And what do we realize? A clock is constructed so that an ideal clock, right? That one is not. Like, look at that one. I want you to look at that one. That one is not the clock I'm talking about exactly because it goes fast, stop, fast, stop, fast, stop, right? But an ideal clock will go na 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 all the way around. And if it was doing that, it is constructed so that theta is a linear function of time. Right? That's how it's constructed, everybody. Right? If you know your angle, you know your time. I mean, like linearly. So it's easy to do a linear inversion in your head. It's 15 seconds, right? We don't make it so that it goes around a quarter of the way, and that's 55 seconds. And then the next 3/4 of the way is 5 seconds. You could do it that way, right? You could, but that wouldn't be helpful, right? So a linear function is kind of helpful that way. So it's a linear function, so I need to write down a linear function, theta of t. So how do we do this? Well, we know the general form of a linear function has the property theta equals mt plus b, right? That's like y equals mx plus b, right? It's a linear function of t, where m and b are to be determined by the problem, okay? Now, I know this is hopefully a little too easy for you, but nonetheless, I want to flesh it out. This is how you construct theta of t. Now, we recognize two things. We have 2 points. At t equals 0, theta is equal to 0. Okay? And if you substitute that in here, 0 equals 0 plus b, that implies that b equals 0, which is great. That's why I chose theta at the top, measured from the top, okay? That's why I chose theta measured from the top. If I had chosen theta measured from the side, you would see all sorts of negatives and shifts by pi over 2 and all that stuff, and it might get algebraically ugly. But you could still do it. You could still have measured theta from here. But theta would be increasing in its negative sense if you had measured it in the counterclockwise way. But nonetheless, we didn't, so you don't have to do that. And the other point is that at t equals 60 seconds, theta is equal to, well, it's come all the way once around, and we know theta is equal to 2 pi. So what does that mean? That means that m is equal to 2 pi over 60 seconds. And notice this has a feature which I always try to emphasize, which is that m has units of reciprocal time. M has units of reciprocal time, okay? It has units of reciprocal time in a very natural way. It is 2 pi radians, which is a dimensionless number, divided by 60 seconds. And this is a frequency. This is also called the angular frequency. Angular frequency of the clock. Of the clock. Okay, so for those of you thinking about frequency in maybe your physics classes, that's where it comes from. Okay? Now, we substitute that theta, which is now a function of time, into the original problem, and we have x, which is a function of time. We have the parametric form of x. X of t is equal to r times the sine of 2 pi t over 60 seconds. And I like to keep the 60 seconds there so you know that t has to be measured in seconds, because you have to have seconds over seconds to cancel one another out, because cosine has to have a dimensionless argument. And y of t equals r times the cosine, did I have that right? Times the cosine of 2 pi t over 60 seconds. So this is the parametric form of a circle. This is the parametric form of the circle whose of radius r, okay? And its particular parametric form has physical meaning, which is it's the circle that's subtended by the second hand, okay? So the curve itself is not the arrow, it's just this thing right there, okay? It's just this thing right here. And we have that t is greater than or equal to 0, less than or equal to 60, but that you don't even need this restriction. That's just once around, right? That's the once around circle. In fact, I would go like that, just to be careful. That's the once around circle. But you could go the twice around, and we know we have the, I don't know how many billions of times around we have in our circles, okay? Okay, that's a circle. By the way, that's a circle over there. The x equals r sine theta, y equals r cosine theta. That's the same circle, right? For theta goes from 0 to 2 pi. But this is more substantive. Okay, and this is not a circle. This is a terribly drawn circle. Okay. Now, this is all nice in 2D, and we're going to actually start working in, I'm going to start jumping between 3 and 2D as is necessary, okay? Because that clock exists in 2D, in 3D. It's just going around a circle, but that circle is in 3 dimensions, so to describe it, I have to tell you where it is, okay? At what z it is. It's up there somewhere. At what y it is, etc. Okay. So the vector representation of a curve in R3 or R2 is simply the following. If I have a curve in R2, often I will call the curve gamma. This means the curve is given by r vector of t, which equals x of t I hat plus y of t j hat plus z of t k hat. So in 2 dimensions, I need an x of t and a y of t. In 3 dimensions, I need an x, y, and a z. I need all 3 coordinates. And I have a parametric form for each of these. And when I write it as a vector, the vector is simply take the x parametric form multiplied by the unit vector in the I direction. Take the y parametric form multiplied by the unit vector in the j direction. take the z parametric form multiplied by a unit vector in the k direction. Okay? You can see how this is important, right? Especially for physics, one of the classical problems that was solved, if this is x and this is y and this is z, one of the classical problems that was solved was projectile motion. Okay? This is a projectile. That's one of the reasons why Newton invented the calculus, right? To solve his force equations. And projectile motion, this is a curve. This is the curve gamma, okay? So this is me trying to throw a baseball. Not a pretty sight. Throw it up in the air, okay? And it's taking this trajectory. When, I'm sure you guys know it's sort of a parabola, almost a very good approximation with caveats all over the place. But nonetheless, let's think about parabola. What is r of t? R of t is the position vector from some origin to some point on the curve at time t. So at time, let's say this vector. So the curve is this thing. This is the curve, right? It's out there. Whoopsh. This vector is the position vector r of t, which says your location after 5 seconds after throwing that ball is there, wherever it is. It has some x value, has some y value, has some z value. So you substitute 5 seconds in there, and you get a number. 3 meters over, 2 meters across, a meter up. Okay? So that's what r of t is. This is the general, very convenient way to think about this curve. And now when we have this nice and convenient way to think about it, we can start doing some calculus. Okay? Consider, now we're going to start doing calculus. So that was just a bit of algebra. Consider a curve so foreshadowing what I'm going to do, okay? I'm about to introduce tangent vectors, okay? I'm going to describe tangent vectors in detail. And I'm not going to get through as much as I want. Obviously, I never do. Then on Wednesday, we'll go into detail about tangent vectors, trajectories, and how you write the equation for a line and what each of the things in that equation means for where that line is and which way it's going, okay? And then we'll do arc length and all of these other things that are parts of Chapter 13. I'm sure you guys haven't looked at it yet because you're thinking about your midterm more than anything else. You're not thinking ahead, but that's fine. So maybe on Tuesday after your midterm when you all got your A's, I'm gonna ask you to read Chapter 13, okay? Consider a curve. Now, I'm going to be very general, okay? And I'm going to draw this curve in 2D, but everything I say applies to 3D. It's only in 2D because you can see that when I start drawing third axes, it starts to get kind of nasty, okay? Everything is in 3D here, okay? So here's a curve. And by the way, this curve, there is no need for this curve to be an open curve. It can be closed. It can intersect itself. You can do whatever you want, okay? So this is going to be like x, and say this is going to be z, y might be into the board, okay? And there's no reason that it goes through the origin also. I tend to draw them so that they're going through the origin. There's no reason that it should go through the origin. But we agree on an origin, a place from which to measure things. We agree on an orientation of the axes. Which way is north, which way is up, which way is east. We agree on that. That's what the coordinate system is. And then from that origin, we draw a vector, which is the position vector at time t. This is r of t. This is the location of that point on the curve at time t. Okay? Now, I use time always in seconds. The book doesn't give units. Calc books don't use units. Okay? I find that to be unfortunate. I think using units makes a lot of sense. You know, you can think of this as a highway. This is a road going through the mountains, right? Where are you at time t? Well, you're on that road. okay? And you're booking at 90 miles an hour because you don't have a sense of your own mortality, okay? But I want you to think of that as like having units, and it's literally position, and it's literally things you have experience with, okay? At a time t plus delta t later, so that means delta t is positive, you are located here. So this is your r of t plus delta t. Okay? Now, you could have dropped a marker at r of t as you drove past, and dropped a marker at r of t plus delta t, okay, and shown a laser from the first marker to the second marker. Okay? And if you could have traversed this, this would be the straight line distance from r of t to r of t plus delta t. Okay? This is a vector. Okay? This is a vector. This is the vector that whose tail is at the head at r of t, and whose head is at the vector r of t plus delta t. By the way we add vectors, what we mean by vector addition, this vector here is equal to, that vector is equal to r of t plus delta t minus r of t. That is to say, if you take this vector, which I haven't given a name to yet, and add it to r of t, bring that over, that's like going up the vector over, that's like going up r of t over the vector who has yet to be named. And that would have been the same thing as going from the origin straight to r of t plus delta t. And so we call that delta r, because delta is used to denote your displacement. Okay? That's your delta r. Notice that this has all the properties we need to do differential calculus here. As delta t gets smaller and smaller and smaller, right? If you go a minute later, 15 seconds later, 5 seconds later, or 1 second later, this delta r, its magnitude gets smaller and smaller and smaller. Okay? But what happens here, also that we know from calculus, that although the delta r gets very smaller and smaller and smaller, the direction of that vector exists. There is some direction to that vector. Okay? So this has all the properties. This has all the elements we used to construct tangent vectors. Okay, so therefore, dr dt is equal to the limit that delta t goes to 0 of r of t plus delta t minus r of t divided by delta t. What did I say? I said the numerator is a vector whose magnitude is getting smaller and smaller and smaller. The denominator is the amount of time after which you measure the second vector. Okay? And we're letting that amount of time get smaller and smaller and smaller. And if this limit exists, it's actually equal to dr dt. What do I mean by this? Well, if you take a look at how I defined r of t is x of t I hat plus y of t j hat plus z of t k hat. And if I take the time derivative, all I'm doing is I'm substituting this whole vector in there and this whole vector in there at time t plus delta t. The I hats don't change, the j hats don't change, the k hats don't change. So what you really mean is you're taking the time derivatives of each of these things individually. So what is this equal to? This is equal to dx dt I hat plus dy dt j hat plus dz dt k hat. And I know, you guys know, because I've been emphasizing all the time, units. The top is measured in meters. The bottom is measured in seconds. You know that this is the velocity. This is the velocity vector. Okay? Is equal to dr dt. Before, I just want to leave you this for the weekend. What we call the speed is equal to the magnitude. So often, by the way, this will be denoted v vector, okay? V for velocity. The speed is the magnitude of v vector, okay? Or that's the magnitude of dr dt, okay? And how do you do that? That's straight up Pythagoras' theorem. First component squared plus second component squared plus third component squared, square root. So there's always a square root in the speed. Okay? That's the magnitude. This magnitude, in general, is not equal to 0. Because I have something, by L'Hopital's rule, I have something getting small in the denominator and something small in the numerator at the same rate. Their limits are going to 0 at the same rate. So by L'Hopital's rule, you have a finite limit, in general. Of course, there are cases where it does go to 0, but the last thing to ask is, what is v vector divided by the magnitude of v vector? This is a vector. This is a scalar. Okay? Consider units. Meters per second divided by meters per second. It is dimensionless. It is unit free. Okay? This is also called the unit vector. Okay, so pardon my use of unit and unit. Units in the sense of dimensions, no meters per second in there. But unit in the sense of 1. That vector, the result of this division, has length 1, is a vector of length 1. And what is it? Well, it is the vector that whose length arises in the limit that this one gets smaller and smaller and smaller. This is the direction vector of your travel. The direction vector of travel. And it's a function of time, notice. All of these guys are a function of time. This direction must be a function of time. It's called the unit tangent.